Hello everyone. We will be conducting a very short experiment today to show what some of the properties of one of the properties of the nitinol material. Before I do so, I would like to just introduce how that works. What is nitinol? Nitinol is a nickel titanium alloy at about 50% nickel and 50% titanium in atomic percentage. And there are different alloys which are named according to the weight percentage of nickel, like the nitinol 55 and nitinol 60. Some of them have different names. They have some chromium, cobalt added to modify the transformation temperatures, and this is a concept that we are going to develop further down in our short presentation here. So the name nitinol comes from nickel, and titanium, Ti, and also the scientific group that discovered it, which is the Naval Ordnance Laboratory, NOL, and a team headed by William Buller and also Frederick Wong discovered that material while searching for material that could be used as tools for dismantling magnetic mines. And here, William Buller, in a Time magazine cover, is doing a demonstration of their finding, and this is a electric circuit, and they are producing the name innovations. We'll further show how that can be achieved with nitinol. And that the importance of nitinol is that it has unique properties. That one is the shape memory effect, and the second one is super elasticity. That material has the ability to remember and return to a specific shape after deformation when exposed to a predetermined temperature. Also, it's extremely flexible material that can undergo significant reversible strain and up to 10%. And here are some of the presentations of that material, which is, here coils of different aspects, more coils, tubes, and you've got plates here. Here are some of the nitinol applications. Some of the super elastic applications at room and body temperature are mostly in the medical field, around orthopedic surgery. You see here a piece of nitinol embedded in a bone, cardiovascular surgery. Here is a clip that is being used during heart surgery, a bit like a stitch, braces, orthodontics, and very well known, maybe out of fashion now, eyeglass frames. You also have sensors and actuators developed and used in the automobile industry, and in cameras. Many autofocus actuators are based in nitinol super elastic properties, as well as optical image stabilizers in mobile phones. Other applications: the shrink to fit pipe couplers used in the aerospace field, in the offshore, self-torquing valves, and safety valves like this, anti-scald valves, showers, springs like this, stronger pull than most steel alloy springs. Applications in robotic fingers, more and more. Nitinol bone plates, which are used in the medical field to keep bones together when broken. And the difference of the older systems made of other alloy, this one is able to keep a constant pull, a constant strength to keep the bones together. How does nitinol works? Well, there is a reversible phase transformation from austenite to martensite and vice versa. And that phase transformation is caused by either a change of temperature, which is a mechanism responsible for the shape memory property, or caused by stress deformation, which is a mechanism responsible for the superelastic property. The austenite phase is called the parent phase, and the martensite phase is called the daughter phase. On that side here, this is what we've seen in previous labs and lectures. It's a steel alloy martensitic transformation, which is irreversible. So you see accommodation here is by slip. And on that side, you've got the austenitic transformation, martensitic transformation of the nitinol. And you see the difference of aspect of the lattice plates. Here it's reversible as opposed to irreversible for the steel alloy. And the lattice plates shift by less than one unit cell, and they maintain the correspondence with the parent lattice structure. A concept which is extremely important when dealing with nitinol, and when an engineer has in mind to use nitinol for an application, must be aware of the transformation temperatures and how they fit his application. There are four transformation temperatures. I'm showing here that graph. Here you've got the percentage of austenite. So it means that, here you got 0 austenite, so it's 100% martensite. And here you got 100% austenite. Here's the temperature axis. So they are, like you see on that graph, various temperatures that I marked as AS, AF, MS, MF. So when we heat the material, the nitinol, this AS is the temperature at which the transformation to austenite starts. Here, this area is 100% austenite again. When the transformation to austenite is completed, that temperature here is called AF. Now, from that state, when we start cooling down the nitinol, we start cooling it out, and it's not from AF really that the transformation to martensite starts. It's from MS, from that point, which is a slightly lower temperature. So MS here, in the process of cooling down the nitinol sample, is the temperature at which the transformation to martensite starts, S starts. And here, MF is when the transformation to martensite is complete. It's important to know that these four temperatures, which are really characterizing the nitinol material, or different nitinol materials, that they depend on the alloy composition and can be adjusted with small composition variation of the order of 1% at the max. So you're probably wondering what these transformation temperature values could be. As you see on this table, each grade of nitinol has got different transformation temperatures. And there is a big range of temperature when you look at that MF temperature, which is here on that diagram, or AS, or AF. You see how they differ from one grade to another. For example, the MF here is minus 53 degrees Celsius. And on that sample or grade number 4, it's plus 24 degrees Celsius. The numbers on this table should provide some assistance when engineering a device which utilizes the shape memory effect. For example, if we design a device to activate at boiling water temperature, which is 100 degrees Celsius, that also must be fully retransformed to martensite at room temperature, which is, say, 20 to 25 degrees C. Highlighted green. This shows here a grade of nitinol which is quite close but not identical to the sample that we are going to use for the demonstration that you will see in a few minutes. Here are some nitinol sample properties. Here the Young's modulus for austenite, Young's modulus for martensite, yield strengths for martensite here, elongation of failure, 15.5% for this particular sample or grade, life cycle. Nitinol has unique high fatigue and ductile properties, which are also related to its martensitic transformation. In the medical field, they are properties favorable for their use in orthopedic implants, for example. So we mentioned that there were two properties associated. They are super elasticity and the memory property of nitinol. Nitinol behaves as like a spring, a powerful spring, and this is its super elasticity property. Super elasticity is when nitinol gets back to its previous shape, and it is very hard to deform. And it is super elastic when its temperature is at or over the AS, which is the austenitic start activation temperature, which is here. How does this work at the level of the lattice? If a stress is applied to nitinol at the temperature above AS, and in that example, for example, here, it's minus 15 degrees. The austenite phase will be converted to stress-induced material, martensite, resulting in a superelastic response. So you see, this is what is shown here. You start with austenite, end up with martensite, stress-induced martensite in this case, not heat-induced, and it's reversible. Increasing stress, decreasing stress. Alloy variations can be chosen depending on desired application, superelastic or shape memory. In this case, we're talking about superelasticity. Here is the tensile curve for superelastic nitinol, designed to be for superelastic applications mostly. Here you got the usual stress strain graph and a coil or spring. You stretch it, then you unload it, and then there's a recovery called pseudoelastic recovery, and the cycle starts all over again, unloads, recovery, stretch. Now, what about the second unique property of nitinol, which is a shape memory effect? Well, we start with the nitinol being at a temperature above or at AF, which is a finishing temperature. Here, about 71, in this example, 71 degrees Celsius. So the crystal lattice are arranged this way. Now we start cooling it down from this point down to MF, which is the martensite finish temperature. So when the material is cool below the martensite start temperature MS, it starts transformation into twin martensite. MF here, 36 degrees Celsius. So we go from 71 to 36 for this particular type of alloy or a composition of nitinol. And it produces a new mode of a crystal lattice, which is a twin martensite here. And below MF, or at MF, about 24 degrees, the material is completely martensitic. And this martensitic transformation is called twin martensite. Now this is the point where they, when you take a piece of nitinol in your hand, you can, especially at that for that type of composition, you can very easily shape it, distort it, and turn it from, say, straight piece of wire into a bundle. Give it whatever shape you want. So you deform it. So because you are doing this deformation, it goes from the twin martensite state to the detwin martensite state. Here it is. Then imagine you heat that bundle of wire that you created. You could give it a shape like a paperclip or whatever you want, a heart. And so you heat it up. And that's where we stand here. You know, we are at MF. We are at AS here. We heat it up. And it goes back to AF, finishing the cycle here. So it returns to the austenite mode here. And the cycle continues over and over. You'll see in a few minutes that very short video. We need to train the memory, or do some memory training, setting a new memory shape. And you'll see we are trying to turn it into a coil. So we are using, for that demonstration, a sample that is designed specifically for shape memory used at room temperature with a moderate accessible transition temperature, which would be around 50 degrees C. And that sample we are going to use now is in its original shape as sold by the lab, was a straight wire. To give it another shape, and again we want to make a coil, it is necessary to fasten the sample with this coil shape and bring it to a temperature which is pretty high, of 500 to 600 degrees C annealing, and then we need to quench it. Once it's that high temp process has been performed, heating process has been performed, then we quench it, and it can be easily deformed by hand and formed back as a wire. And then you will see when it's heated above the transition temperature, the nitinol wire will return to its coil shape, and that's the shape we gave it at high temperature, austenitic state, and with much more force than what was required to put it in shape when it was cold. Here is how we intend to proceed during the demonstration. Here you see the temperature, and here are the different phases that we are going to follow. So looking at the temperature axis here, you've got the MF, represented here 25C. You got AF, 50C, and then it's the point where we do the heat treatment annealing. So when we get the wire, when we purchased that wire, it was in a straight form here, in a martensite structure. Then what we do during that demonstration is that we force it, we fasten it in order to give it the shape, or try to give it the shape of a spring or a coil. So these red dots here are like fastening system. Once this is done, then we are going to heat the wire above 500 degrees Celsius, which is the temperature that we can achieve with a flame. And then we'll cool it down. Here we're not going to slowly cool it down as it's shown. We're going to cool it down, quench it really, and then we are going to release the coil, removing it from its fasteners. And at this point, it's very easy to change its shape by hand. So what I'm going to do is straighten the wire, put it like a wire again by hand, and we'll be putting it in hot water above the transition temperature here, which is 50 degrees Celsius AF. And you will see what happens. Here are some other classic experiments after what we just did, which require a little bit more means here. You have an inchworm, so you have a coil here, you apply some current, and it heats up the coil, and then you release the current, so it cools down, so it eventually will make that look like it's working. Here is another view of it. You see you have a very simple system where you apply current or not. Here is a very, very classic experiment with a paper clip. So that the original shape was a paper clip. Then you kind of deform it, put it like this, and put it back in water, in hot water, and it turns back to be a clip. Here you have a very interesting system, which is a heat engine that shows how to convert heat into mechanical energy. So you see here that's a pretty simple device. You've got the wire, and you've got hot water here, and you have the cold side, which is here. It's a very promising system. Maybe it will be further developed in the future for larger industrial applications. That is another classic experiment with a spring. You don't see very well in this picture, but it's showing how strong the super elasticity effect is on a spring. That concludes our demonstration. Thank you very much.